Hello everyone, my name is Moritz Einfalt from University of Augsburg in Germany, and it's my pleasure to briefly introduce our joint work together with Rainer Lienhart with the title Decoupling Video and Human Motion towards Practical Event Detection in Athlete Recordings. In sports in general, video recordings are a dominant source for performance feedback, either in the form of qualitative assessment by trainers or training scientists, or by an actually quantitative performance evaluation. However, this form of evaluation usually requires either the manual annotation of the video material or some form of automation. Now, among the most fundamental kinds of performance parameters we can extract from videos of athletes is timing information, or with other words, the detection of certain events that can happen throughout a video. And since we are focusing on individual sports here, these events are usually tied directly to the motion of the athlete. Possible questions we can ask ourselves here is, if something is happening in a video, when or where it is happening, how often or with what frequency, as is the case in the example on the right with the athlete and his step count and frequency. Our goal is to build such automation for motion event detection for individual sports recordings with a strong focus on practical solutions, and we give examples for swimming as well as athletics. In order to automate event detection for performance evaluation, we need to find practical solutions that are specialized to a specific domain. This is because practitioners usually have rather high precision requirements before actually adopting such an automation tool. And at the same time, the solution also has to cope with limited data and often also limited time and budget. This makes rebuilding a complete and full stack vision model that directly maps from the vision or video domain to the domain of detected events simply not feasible, as we would have to do it for every domain again and again. Our main proposal now is to decouple the low-level vision aspect of the problem from the actual human motion we are interested in. And we therefore build on the state-of-the-art in human pose estimation to capture the actual motion of an athlete in a video by an estimated pose sequence, and use this as a rather compact and intermediate representation that allows to build much smaller and simpler event detectors that can more easily be specialized to a specific domain. The state-of-the-art in 2D human pose estimation are still single image, or for videos, single frame pipelines. Given a recording, for example the underwater view of a swimming pool, single frame processing will lead to many detections and poses over time, including the athlete of interest, as well as other athletes and bystanders. Therefore, we need some form of temporal tracking to identify the single sequence of detections and poses that belong to the athlete of interest. For this, we propose a simple track, merge, and rank framework that can easily be adapted to the domain at hand. First, given all the detection throughout a video, we build initial tracks on generic detection statistics like overlap and scale of the person. Then we merge temporally closed tracks to account for detection gaps. Finally, we rank all resulting tracks according to domain-specific objectives. Depending on a scenario, we might have information about the expected scale and position of the athlete, his velocity and direction, or his time of appearance in the camera view. And all these objectives can be incorporated into the ranking mechanism to select a single track belonging to the athlete of interest. Given the pose sequence, we introduce two quite different approaches to event detection, depending on a scenario. The first application is event detection in swim start training. In this setting, swimming athletes are recorded by a static multi-camera array over and underwater, parallel to the swimming pool during their swim starts. Here we only have a very limited number of annotated recordings, and the motion events we want to detect are rather sparse and only occur once every recording. To account for these circumstances, we introduce a framework of very simple decision rules that decide on event occurrences based on the pose sequence. And we describe it for three different types of events. The first are position-based events, where a specific body part surpasses a fixed location, for example the head surpassing the 10-meter mark for the first time. Second type are presence-based events that occur when a body part is visible for the first or the last time in the camera view. For example, the head submerging underwater, marking the moment of the dive-in. The third type are pose-based events, which can be detected based on extracted features from the human pose itself. For example, the occurrence of the first minimal knee angle after the dive-in, marking the first underwater kick. And all these decision rules have only very few parameters that can be optimized even with the very limited data at hand. For our second scenario, the event detection in long and triple jump recordings, we propose a different approach that reflects the much less restricted circumstances. Here we have recordings of an athlete from a single panable camera mounted at the side of the running track. And since the position of the camera can vary, we observe poses from different viewpoints and scales. Our goal here is to detect every begin and end of ground contacts, leading to the two event definitions step begin and step end. Additionally, here we have much more data available, and each event occurs multiple times per video. This enables us to directly learn a model to map pose sequences to event occurrences. For this, we adopt the notion of a continuous pose sequence translation from previous work. The idea is to learn a model that predicts a timing signal at every time index of the input, and this timing signal should be 0 at the event occurrences and otherwise should encode the estimated duration until the next event will occur. To solve this sequence translation task, we employ a temporal CNN that directly operates along the temporal axis of the pose sequence. Its architecture follows the generic TCN architecture for general processing of 1D time signals. In the paper, we specifically consider the questions of appropriate pose representations and normalizations, as well as data augmentation strategies that introduce realistic error modes to simulate imperfect pose estimates. We evaluate our approaches in two datasets. For swimming, we collected 105 recordings from swim starts at 50 Hz with 6 different events annotated. Only 23 of those are actually used to optimize the decision rules. For long and triple jumps, we collected 167 videos at 200 Hz, which were fully annotated with respect to the two events step begin and step end. With 117 videos used for training, we obtained a sufficient set of annotated event occurrences to train our CNN-based sequence translation. For pose estimation, we used a high-resolution variant of mask RCN, which we fine-tuned on 2,000 to 3,000 pose-annotated frames taken from non-test set recordings for swimming and long and triple jump. Finally, for evaluation, we measure event detection performance with a precision recall and F1 score at a maximally allowed deviation of delta T frames. For swim start training, the table on the left shows the F1 score of event detection at frame thresholds of 1 and 3. Even at the very strict evaluation at delta T equals 1, we achieve over 90% in F1 score on most of the event types. So here we allow only at maximum 1 frame deviation between the annotated and the detected event. At the relaxed evaluation, at delta T equals 3, nearly all events are correctly detected with a score of over 97%. The only exception to these results is the detection of the first underwater kick, which saturates at about 90% in F1 score. This event coincides with the video phase with the most challenging visual conditions, where a lot of bubbles are in the water from the dive-in. This leads to disturbed pose estimates for many subsequent frames, and due to the very simplistic rule-based event detection, the first kick sometimes does not get detected at all. For long and triple jump, the combined results on detection of step begin and step end events are shown in the right table. Starting with a baseline model of the CNN-based event detection, we achieve similar results to swimming, although at 4 times the temporal resolution due to the 200 Hz videos and pose sequences. However, when we include the additions of pose normalization and augmentation as discussed in the paper, we can greatly enhance the performance to up to 97% in F1 score at a maximal temporal deviation of only 4 milliseconds, leading to a highly reliable event detection system. Finally, here we can see some examples of detected swim start events: the jump off, the dive in, the first kick, and the arrival at the 5, 10, and 15 meter markings. As discussed earlier, only the first kick on the water shows systematic misdetections, where the detection actually belongs to the second or third underwater kick. Here we see some examples for detections of the step begin event in a triple jump and a long jump video. The plots on top show the dash ground truth timing signal, which the CNN-based sequence translation can recreate quite well. Discrete events are extracted at the 0 points of the predicted output signal. As we can see, the events are correctly detected, even though the 2D poses can look quite differently depending on the camera viewpoint and the phase of motion. On the right, we see one of the very few misdetections resulting from a failed pose tracking over a longer period of time. To summarize, our main proposal was to use pose sequences as a compact motion description. It facilitates the design of motion event detectors in individual sport recordings. We presented two different approaches. For very rigid scenarios, we manually design and optimize decision rules, and this can already lead to a sufficiently performing event detection. For less restricted scenarios, a CNN-based sequence translation model can be employed for a highly accurate motion event detection. Our evaluation showed convincing results on the two domains, but the general ideas are transferable to other individual sports or events.